My name is Mark Hazzard, and the title of my project is Composite Protection from Atoms to Application. And my supervisors are Paul Curtis from DSTL, Lorenzo Iannucci from Imperial College London, and Stephen Hallett and Richard Trask from here in Bristol. The aim of my project is to generate novel hierarchical composite fiber architectures for improved impact performance. In particular, I'll be looking at trying to reduce perforation for a particular areal density and control backface deflection. And in order to do that, I'll be trying to take some inspiration from nature and looking at things like the horse's hoof or teeth, which have a lot of their fiber architecture in the through thickness direction near the surface, or other things, for example, like exoskeletons, helicoidal architecture, and they're trying to use energy absorbing mechanisms in the delamination to maximize the energy absorbed during impact, as well as being able to limit backface deflection. And in order to do that, I'd like to use finite element analysis to drive forward the design. And this initially required some materials testing in order to build my material card ready for input into that model. The material that I'm particularly interested in is ultra-high molecular weight polyethylene fiber composites. The reason why I'm interested in these type of composites is because they have the highest specific energy absorption, as well as the highest, one of the higher extensional wave speeds. And when you look at this Ashby plot, they're high and right on the right-hand side when you compare them to carbon fiber or S2 glass. And when you multiply extensional wave speed with specific energy absorption, you get a high kind of C star parameter, which is a very good indicator of ballistic performance for composites. They're also extremely damage tolerant, so when you look on the SEM on the right-hand side, that is one of the fibers over a knife edge. So how do these get manufactured? The fibers are initially gel spun, and they're combined with a polyurethane matrix, so just rubber, and UD plies are cross-plied in a 090-090 configuration by the manufacturer DSM. And the reason they do this is because the plies are very, very thin. And if you have a UD ply and you hold it in your hand, it's quite easy for it to fall apart. So the cross-ply in the SEM, there's an SEM of the cross-ply as it arrives on the left-hand side. I then hot press these together, or lay them up and stack them and hot press them in a group at about 120 degrees C at 10 megapascals, 20 megapascals, and 30 megapascals pressure. And in the end, I get a volume fraction of about 83% of fibers with a ply thickness of about 70 microns. And one interesting thing I saw in the SEM was that I got some fiber indentation, which you can see on the right-hand side between the layers due to the hot pressing. So that's why I investigated the different processing pressures to see if that had an effect on any of my material parameters. So initially I started with shear testing by doing plus or minus 45 tensile shear tests. And as you can see, the result's highly nonlinear. And this is because the result is dominated by fiber realignment towards the loading axis. The higher manufacturing pressure led to a slight increase in shear strength, around to about 20 megapascals. And the initial stiffness was around 86 megapascals. So a lot lower than what you think or what you'd compare to carbon fiber epoxy. I also did a quick investigation on the increasing strain rate, and I noticed about a 50% increase in stiffness due to an increase in strain rate. I then went on to do some tensile testing, and the low shear properties dominated my tensile testing. And as you can see, that I have to do custom tensile specimens in order to get the load into the gauge region in order for it to fail in a tensile manner. And as you can, it did fail in the tensile manner in the gauge region, but at the rear of the specimen, I noticed some pull-in of the fibers from quite a large distance away, and this can be seen in the image in the center there. Below this, I then went and did some microscopy of that region, and you can see, again, the fiber reorientation towards the loading axis. And further to the right, you can see lots of intralaminar slip and intralaminar shear between the matrix. This led to a variable stress state in my gauge region, which meant I was unable to determine the effect from fiber indentation. In the future, I'd like to use my test data in order to input that into some explicit finite element analysis. And I'd like to use this model to drive forward the design in particular looking at some parametric studies, seeing what material parameters particularly are very sensitive to absorbing the most amount of energy under impact. And then I'd like to optimize my design accordingly. As an example, you can look on the video on the right-hand side. I might want to increase shear properties on the front face of an impact, but increase the membrane properties on the rear in order to maximize energy absorption for a given aerial weight. Finally, I'd like to thank all my supervisors for their help and my sponsors, DSTL and EPSRC, and thank you very much for listening.